Yes. So today we discuss the structure of time in European tradition, cultural tradition. In European tradition, time is segmented in three segment sectors, parts: present, future. So the idea of time is that this is a one-dimensional arrow, so to say. Okay, this concept had been developed only in 17th century, essentially by Newton. Leibniz, who actually lived at the same time, believed that time is something relative to events. There is no, continuous arrow. So this is a new idea. Actually, this is the idea of Europe. This is a contribution of European culture to the whole humanity. What did they discover? They discovered that they discovered the particular model of time. In different cultures, time is different. Sometimes it's even almost not existent. I should say that, for instance, I was very impressed by Chinese understanding of time, when if you just switch on a Chinese TV, you always see fantasy movies about Second World War, about some faraway past, I don't know, dragons, kings, princes. My famous movie is Journey to the West, you know, from the story from Ming Dynasty. And well, you see that there is no concept of future. There is no fantastic movies, for instance. It's a fantasy, you know, Herr der Ringe, so Lord of the Ring. Lord of the Ring, it's fantasy, it's not a fantastic movie. It's something about, you know, about something which never existed, some of the past, but basically about the past. And most of cultures in the world don't have this understanding. So what do we have? Let us suppose that we have a time series. At each moment of time, I have some value. I'm able to observe this time series for some time. And finally, I was able to got some ideas about how often particular values could be observed. So in another word, I can say, okay, so I take to make a laser pointer. So I know the probability of every event to occur. Then I can calculate what people call Shannon entropy, which assess the amount of uncertainty of a particular event. And this amount of uncertainty, once it's released, when the event had occurred, appear to be the amount of information you gain once this uncertainty had been removed. Okay, it turns into an information. Westerners believe that once they split a sequence of events into three segments, past, present, and future, there are four different types. So what does it mean, basically? The question, what does it mean? A European time concept. They believe that there are four different information quantities. First quantity is information transfer from the past to the present. We decided something, and then we made a plan, and then we realize it in present. This is an example. So it's called, in philosophy, European philosophy, it's called downward causation. Downward in the sense that there is a overall, I mean, the global structure, your plan, or whatever, law, and it predetermines the present behavior. There is another information transfer upward causation. How you could design your own life. Is it possible? Do you have a free will? So here in the United States, people believe that they could. And therefore, many people come here because they believe that they could change the life of their families by investing a lot of efforts now and at present, and in the future they would have a house, a family, happy children, and so on and so on. Okay, so it's called upward causation. This is your free will, so to say. Then there is a direct transfer from the past to the future. This blue arrow. It tells us, it describes particular situations when, for instance, some laws, it had been, or constitution, okay? It had been taken, I mean, it had been written 2 centuries ago. And nevertheless, no matter what would happen in November, somehow these norms would still working. This is another type. It's just, the direct transfer from the past to the future, irrelevant to what's going on now, at the present. And finally, the fourth amount of information is so-called ephemeral information, which happens occasionally now, being of no consequence. It's not a consequence of what's happened before, and it has no any repercussion for the future. It's simply something which happens now, a randomness. Okay, so this is what Europeans believe is time. Time is. Okay, so that is what they think. And in principle, they describe their vision, or our vision, if you accept it, in terms of information theory. So all these 4 quantities somehow are incorporated in these in the Shannon entropy, in the information. Namely, they simply, I could decompose, that's what I will do all time today. I will decompose this Shannon entropy into some information theoretic quantities. Why I think it's important? First of all, because we last time we discussed about random walks on graphs, databases, some data arrays, and whatever, on some similarity matrices, thinking that this is a machine learning. Now the question is, in fact, we can, even if I have some database or a graph, and I perform a random walk learning this graph, the outcome of my observations is a time series. I visit node by node. So some nodes which I passed by, they are my past, in my past. Now the present node is my present, and the future nodes where I would visit next time, I mean, well, in the next steps is my future. So, well, now, if you read some books in information theory, you might see expressions like what is shown on this slide. Don't be scared, don't be afraid. First of all, these quantities only express a symbolically what I already tried to explain you in the last slide. Okay, this is our conceptual understanding. The fact that I wrote some formulas does not mean that these formulas could be always calculated. These quantities, for most of cases, are unknown. For most of predictions, these quantities are miscalculated. Just erroneous, okay? But nevertheless, in some cases, for instance, for random walks, Markov chains, stochastic matrices, it's possible to calculate them directly for any graph, for any musical composition, for, for time series, for stock markets, and so on and so on. So that's what I'm going to show you today. Now, what is the meaning? I'm just trying to describe the meaning of each arrow here in terms of information theory quantities. So the first information between the past and the future conditional on the present. That means it is independent of the present. Present exists, but it does not contribute to information. So this is a direct bridge from the past to the future. It's a sum, accordingly to information theory, or rather set theory, because it's one and the same. You see, it's a sum of uncertainty of the future state given the present, and uncertainty of the present state given the past, minus the uncertainty between the past and the future given the present. Okay, I just conceptualize what I think about this information transfer. Downward causation. It's the information between past and the present. So it's uncertainty of the present state minus what people call an entropy rate. It's uncertainty of the present state conditional on the past. Conditional on the past means that it doesn't depend on the past. Something happens now. Okay. Now, upward causation is the information between the present and the future, conditional on the past. So it could be decomposed as actually uncertainty of the future conditional on the past minus uncertainty of the present conditional on the past. And finally, the ephemeral information, uncertainty of the present conditional on the past minus information, well, actually between the present and future conditional on the past. That is from where it came. It's basically what we think, what Europeans think about time. In different cultures, there might be different conceptualizations of time. In many cultures, time is cyclic again. And it means that the conceptualization of time in that case would be completely different. And quantities which might be extracted, information which might be extracted from other models of time might be different. It depends upon customer. In some cultures, your project would be okay. In other cultures, your project would be completely, unsustainable and meaningless. Now, okay, yes. Now for Markov chains, because we worked always with stochastic matrices which define some kind of a random walk or a Markov chain. The situation is a little bit simpler because here the conditional information, the uncertainty between the past and the future conditional on the present equals the same quantities as I have here. As a result, I have zero. There is no, you remember that in the Markov chain, I always have a transition matrix, which is constant. It does not depend upon time. So walkers from the past arrives at the future only through the present, applying one and the same matrix. It means that this information quantity, direct jump from the past to the future, is impossible for Markov chains. It's zero. So I only need to go through the present. And this picture dominates the Western understanding of time. And even the guy who, Andrei Markov, who actually invented these Markov chains, worked in this paradigm. Okay, he simply conceptualized what people of his environment, I mean, all these European people, thought about time. It's not a law. You should understand that. Because we now enter, well, in many fields where we observe very strange phenomena, which are not described in our usual language, or not compatible with our usual understanding of the universe. So you should be ready that you might discover or observe something which does not fit these standard ideas. Okay. Now, well, so for Markov chains, we have only three processes: downward causation, ephemeral information, and upward causation. Now, These quantities, one by one, can be translated in terms of transition matrices. Matrix. If I have a transition matrix, any row stochastic matrix, which can describe me transitions between anything. Okay, it might be some normalized affinity matrix. It might be some normalized matrix of similarities or whatever. I have then immediately some transition matrix, and as soon as I have a transition matrix, I know I can calculate just immediately quantities, information quantities which are transferred from the past to the present, from the present to the future, which are also dissipated at present. So present, what means present? Present means that some amount of information, ephemeral information, is dissipated, created and dissipated instantaneously, having no any consequence for the future. You used to think in terms of this literature about, butterfly effects or whatever. Something happened in the past which changed completely the image of the future. No, it's a complete bullshit. Stop thinking about it. This is a bullshit for earning money, nothing more. There are a lot of information which created in the present and dissipated without any trace and consequences. That is the actual real life. Okay, so you can calculate, I'm just give you the answer, so to say, but in principle, it's possible to find it. Okay, now, example, coin tossing, a simplest example of a Markov chain. A biased coin. In a usual coin, I have two states, head and tails, which change each other with probability 1/2. But this is indeed, kind of a fairy tale. In reality, every coin is biased. Even your technique, how you are going to throw it, to flip it, creates a bias. So some state might be repeated more often than another state. In my simplest case, just to give you an idea what I was talking about a few minutes ago, I mean, in the last few minutes, I just consider a very simple scheme in which I have 0, 1, 2 states, head and tails, which might repeat each other with probability p, and with probability 1 minus p, I have the change of the state. P might change from 0 to 1. If p equals 0, I have actually, then each state, I mean, the states do not repeat each other, do not repeat. So I have 0, 1, 0, 1, 0, 1, simple alternating sequence. Okay. If p equals 1, then the situation is the opposite. The states repeat itself. If I am at 0, I would, I would actually confine in zeros at 0 sequence forever. And the same about 1. If I occurred at 1, I start at 1, I continue. Now with probability 1/2, I have the fair coin. It might change and I cannot predict, right? It's fair. I cannot predict what's happened next. But if P is not 1/2, in all other cases, you see, I can predict. And we will measure these information quantities. First of all, the transition matrix for my problem is simple, P, 1 minus P, 1 minus PP. Okay, so in principle, this is an arbitrary, for me, it's an arbitrary stochastic matrix. It could represent any database. Again, it could represent the urban structure, because I know which place is connected to which within a city. I just look at the map, and I can write down these transition matrix. Okay, left eigenvector for this row stochastic matrix should give me the stationary distribution. The stationary distribution here is 1/2, 1/2. So the probabilities of tail and heads are 1/2 uniformly, no matter what P is. Because, even if I have P equals 0 or 1, it means that but I could choose between head and tails initial step with probability 1/2. Okay, that's the reason. I always have 1/2 here. Okay, so that is the uncertainty. 1/2 in sense, if I calculate it with respect to logarithm on base 2, like Shannon did in his information, it gives precisely 1, and people call it a bit of information, 1 bit of information. So coin tossing of a coin, the outcome of this tossing gives me a single bit of information, head or tail, okay, yes or no. It's a single bit of information. Whenever you have some complex message, you can nevertheless decompose it in some binary situations, questions, and the amount of bits which comes from this decomposition, this is the amount of information encoded into my message. Now, so independently upon the value of P, of my bias, the single coin tossing reveals a single bit of information to me. Now I will calculate the entropy rate. Entropy rate, if you remember, this is how future, I mean the future outcome conditional on the present, independent on the present. So it's what's happened during a single flipping event. So I can calculate it, and the general formula as a function of P is here. It's a kind of, it's in fact, well, a parabolic curve, which attains maximum at 1/2, but which is 0 as P equals 0 or 1. And the meaning of these 2 points, 0, P equals 0 and P equals 1 is clear. If P equals 0, I have a simple alternating sequence of zeros and ones. And for P equals 1, I have repeating sequences. For me, the both situations are completely predictable. So the quantity which is colored here by red or pink, this is downward causation. The complete bit of information which could be revealed by flipping a coin, if P equals 0 or P equals 1, completely predictable. Okay? If I have a repeating sequence, I just observe, I have 0, 1, 0, 1. What is the next, you would ask me? I say, okay, I had 0 just now. Okay, so I should have 1. And I will be right. I completely know the outcome. The situation is completely predictable. The same if I have a uniform sequence of zeros and ones. You ask me, what is the next? I tell you 0 or 1. And everything is predictable. Everything is clear. This is a completely deterministic process. But if I, for instance, take here 1/2, and you would ask me, what is my, say, what would be the outcome, I wouldn't say you anything. Okay? Now, however, if P is a little bit greater than 0 or a little bit less than 1, my ability to predict the next symbol from by observing the whole sequence from the downward causation, right? I observe the whole sequence and tell you, okay, I know the next outcome, right? But if my probabilities becomes greater than 0 or less than 1, then indeed my ability to take information from the whole sequence fades out. I'm not able to do it, but nevertheless, the very last symbol becomes important. And it gives me the upward causation. For instance, if P is increasing slightly greater than 0, I can say that, okay, well, I can't say anything about from I can say not that much from the overall structure, but since I just had 0, so probably next time I should simply repeat my guess. Okay, if P is less than 1, I should say, okay, but before I had 0, now I might alternate my guess and get 1. And in some cases, I would be right. I would be correct in my prediction. So finally, this upward causation, if I calculate it, if for this biased coin takes the following form, so green amount is predicted, red amount is predicted, and only the purple amount is ephemeral information, completely unpredicted. And you see that here, why actually I have a biased, I have a fair coin at p equals 1/2? Because I have two contradictory hypotheses that I should repeat the symbol and I should alternate the symbol. So I have kind of destructive interference of these two hypotheses at the center, precisely when p equals 1/2. So namely precisely of this situation, I'm not able to predict what happens if the coin is fair. Okay, so I didn't invent anything. I simply explain you what European cultures thought about things about time. Okay, so that is the world which had been created by them, by us maybe, right? But which runs here. Okay, now well, so and concerning the purple, so this is ephemeral information, basically information component existing only in the present moment, being neither a consequence of the past nor of consequence for the future. It's just the amount of information which disappears from your life. You did something, but it creates nothing. I mean, there was no outcome of your efforts. Okay, so well, remaining quantities, portion, yes. Well, okay, so that's what I already. So the formula for ephemeral information is given here. Well, it's simply a calculation based on the transition operator, on the transition matrix. Well, and this is just a representation of. So just if you look at this, so finally, what's going on? Typically, so it means that the information amount which would come from the flipping process could be decomposed. So it's called information decomposition into predictable and unpredictable components. Predictable, it depends upon, well, if I have the system of P and Q, this is a function of P and Q, and I have these pictures which I explain in a second, but indeed, these quantities depends, P and Q and U, predictable and unpredictable information, depends upon probabilities to repeat the symbol. Okay, even if the amount, information amount is always the same, this decomposition might be very different. So if you want to, for instance, I mean, in the last picture, I'm going to show you how to work with stock exchange, stock indices, basically, because they allow different predictability. So some people prefer to invest into predictable regions. Others are used to invest in unpredictable regions because they believe that they can remove money at proper time. Okay, so but okay, so if for the case of two P and Q biased coin, then I have a symmetric picture. The gray volume is the amount of information as a function of P and Q. Then the amount of predictable information for, you know, could be seen as a kind of a saddle within this information profile. And then finally, I have the remaining part is unpredictable information, which is indeed inside this, how to say, this figure of the total information or total uncertainty. But some part you could predict, another part you cannot predict at all. Again, just a representation of the same information in the form of a pie chart. In fact, whatever happens at present, well, it contains some uncertainty. There is the uncertainty of the present. Okay, it's a total amount of information. It could be decomposed in something in uncertainty emerged now. And the difference between the total uncertainty and uncertainty emerged now, it's called a downward causation. This is the part of event which is predetermined by the structure, by the data. It could be understood from the data. When you are asked to perform a data mining operation, to learn from data, that is the part you can learn. Okay, now also there is an upward causation. So this part you can learn from the overall structure, and this part you can learn from the actual behavior of individual now, or actual event what happened now. For instance, the war had started, how it would change the oil prices. Or it changed the oil prices to extent that there was a general demand from economy. It's a downward causation. And this is a concern about war. This is an upward causation. This part you can estimate. This part you cannot estimate at any, whatever you do. It's completely unintelligible. In some systems, this unintelligible amount of ephemeral information takes the whole available information, and you are not able to learn from the data, and vice versa. There are some very good situations for us when we can learn from the data almost everything. Okay, so this is my message. And don't try, if you see that the ephemeral information takes 90% or, you know, a lot of, most of uncertainty is just the ephemeral information, you would never understand, well, its reasons, just a garbage. Okay, now, and this is also the information not captured by the present, but for the Markov chains, it's just zero. So ephemeral informations, what emerges now and disappears without a consequence, downward causation, long-range correlation structure determine the present. The social status of some families determine the future of their children, you know. That is what the downward causation means. Upward causation, what emerged now and has repercussions in the future. This is what you can do for your future. This is what your family can do for your future, if they can. And ephemeral information, this is a black swan, which might happen, but might not. Okay? Now, well, in principle, since we have a triple decomposition of uncertainty, I can use this radar diagram for every component, and I have that, for instance, for coin tossing. If I start P from 0 to 1/2, the downward causation, its amount reduced, and then I get the most information as ephemeral when the coin is unbiased, fair coin. But then when P goes through, passes by 0, 1/2, goes to 1, finally I get back, I'm going back, and then downward causation determines you everything. Now, since I have a random walk, I can calculate all these quantities for any structures, graphs, and databases. And in the next, say, well, 10 minutes or something, I will just show you these examples. Okay, so labyrinth, maze, okay? So what do I have? Basically, if you look at this maze, you would see that this is a tree structure. If I enter a proper corridor, I immediately get out, sooner or later. Well, not immediately, sooner or later. If I enter if I enter not the proper corridor and choose not the proper road, I can end up in a dead end. Okay, so here I can if I calculate the downward causation and ephemeral information and upward causation as a function of length of equiprobable path. You remember last discussion about anisotropic walks.
So it's just, it means that I change the resolution of my, my glass, looking glass. I just change the resolution and observe how much information I could get at every resolution. And my information means 3 components. One component which I can predict from the overall structure. Another component which I can predict singly from what's going on now. And third component which I cannot predict by any means. So, and you see that in a structure like that, I have basically the very simple picture. The overall amount of information goes down, reduces, goes down once I decrease the resolution of my approach. And everything is smooth. Downward causation dominates all the decisions here, because in fact, there is a single corridor which I should follow, no matter where it goes. If I have more interesting cases like Venice, channels of Venice, here I have a very interesting oscillations. So at different resolution, I would get different amount of information. And in particular here, I just draw a radar diagram for using the random walks T1, so this nearest neighbors, usual random walks, isotropic random walks, and T infinity, having in mind this Ruel-Bowen random walk of maximum anisotropy, what I shown you. And here I see that for T1, I have the downward causation dominates the information decomposition. And for T infinity, I have ephemeral information which dominates the composition. The structure is chaotic, I should say, in large scale. In the small scale, it's fine. You know, everything is predetermined where I go, basically. Basically, the Venice is the composition of 7 families who had actually excavated these channels to split the territory and to bore, to be, how to say, to limit the advancement of other families. Okay, so that is basically how history changed our mind. Manhattan. The situation is also quite interesting. There are oscillations in all quantities. And if I analyze the structure, ephemeral information dominates at all scales. Now, so that is the question: which scales are the most informative? Now we have we harnessed these information theory tools, and we can answer this question precisely. So you see that if I change the resolution, at some point I'm able to understand what's going on, and after that, no, nothing. Okay, so in principle, it's possible just simply to calculate a ratio between information, which is, the entropy rate, and the excess information. So it tells us in particular how downward causation is important, whether it's important or not. And it appears that, for instance, if there are some structures, there might be peaks, some particular resolutions at which a system, a data, might give you some non-trivial information outcome. Otherwise, if the structure is confusing, so to say, like in a maze, in a labyrinth, then this ratio, this fraction simply goes out to 0, decreases to 0, without any peaks. So in principle, you can estimate the amount of information in the data, and you can catch the particular scale, important scale at which it might be reasonable to study the data. Okay, so that's what people do in this case. Indeed, not many organizations, so to say, perform such a deep analysis. Mostly, I have in mind actually what my experience of working in China. They already had all solution. They had their mindset. They already knew what should be the outcome, what should be the solution. They were interested in their and the United States situation is just all these FBI and other guys. They are simply considering that they know better. They just want the data analysis to support their claims, nothing more. Okay, now we could apply the same methods. We could apply the same methods for analysis of time series and musical compositions and whatever. For instance, musical composition. In MIDI file, you have representation. There is a MIDI library in the internet. You can download thousands of different musical compositions. And then you could calculate the number of times one musical note follows another one. You could construct the transition matrix. This is a transition matrix for horn concerto of Mozart. So these are different probabilities. If it's red, it's very low. If it's blue, it's very high. So you get a fingerprint of its structure. And then you can calculate estimate the ephemeral information at different scales. So in large scales means infinitely long sequences. Okay, infinitely long path. Downward causation dominates. It means that there is a structure, scale, musical scale tonality scale, okay, of particular musical composition. So there is a structure on global scale. And on small scale, we have upward, yes. So we take the musical composition, several thousand notes, and then count how many times we observe a transition from C to D or whatever, you know, from do to mi in Italian European tradition. Well, we just counted with respect to the all other transitions, thousands of transitions observed during the composition. So you get a transition rate, I mean, a real transition matrix, transition rate from every musical note involved in this composition or not. So you see that there are some gaps. It means that some particular notes had never been used in horn concerto number 4, but it might be used in some other. So you see that on the small scale, we have upward causation dominating. So the kind of, you know, creative, how to say, force or talent of Mozart, precisely. How on a small scale, he was able to vary the structure. Globally, it was predetermined by tonality scale, but locally, yes, indeed, he can do something. Okay, now I go further. Right, so Beethoven, Furelise. La 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 la, and so on. So this is the transition matrix, and downward causation dominates all scales. So the structure, why it's so melodic, why it's so, how to say, sticky? Simply because it's completely, you know, following the same ideas on all scales, and people feel it. Tchaikovsky seasons. Again, on downward causation, well, it's every musical composition because it has some tonality scale. Indeed, the downward causation would dominate the long sequences, but on short sequences here, you see that it's almost, I mean, equilateral triangle. What do I have now? Oh, concerning the phase-space dynamics, Standard & Poor's, so it's in fact the economic indices in the United States. So we have 500 firms roughly 498 or something. 500 firms included into Standard & Poor list. And we can calculate the return roughness, and then, for instance, this is for Amazon company, this is for Apple company, prices, return and roughness, so coordinate and velocity performs some kind of, you know, oscillations or movements around the center, around zero. So the stock prices go up, go down, go up, go down at different velocities, but nevertheless, it's still kind of oscillations. In principle, it's possible also to construct a phase portrait of the American economy, information content of a cell and so on, but it's just, you know, from more detailed presentation. That's the picture I want to show you. So this is the information decomposition. H is the Shannon entropy, uncertainty, expressing the uncertainty of price of a company. And using since we know now how often a price, a stock price jumped from one cell of a phase space to another cell, we can calculate the transition matrix. Since we calculate the transition matrix, we have these three components. So the Shannon entropy is represented by three components: downward causation, upward causation, and ephemeral information. Downward causation means that particular prices are predetermined by the history of the market and probably the situation in the economy, global situation of the economy. Upward causation, how current present event, what's happened now, kind of presidential election, war, some news, how it predetermines the future outcome. And finally, there is ephemeral decomposition, just, you know, randomness, random luck, or vice versa, how to say, well, disaster on the market, which might actually affect the prices. So we can, for every firm, we can decompose the total amount into these three components. And these three components of the market are drawn here. So here are some quantity. So for each firm, I have some quantity as a downward causation, some quantity as an upward causation. These two parts could be predicted. This is by observing the whole series, and this is by particular analytics from the particular firm or from particular local situation on the market. And this part cannot be predicted at all. So, and you see that there is a clear tendency. Well, okay, so the more predicted information I have here, the less unpredicted information I have. But basically, you see that the less unpredicted, the higher is the uncertainty of daily stock company, the less is the unpredictable information. This is not a surprise. If I have a high uncertainty, it means that the price has a high mobility. It goes forward and back, forward and back, forward and back, forward and back. I collect a lot of statistics about this price, and I can predict. The more I observe, longer I observe, and the more mobile and active are the prices, agile, so to say, right? So the better I can, the better I can study them and predict, and vice versa. If I have something, you know, the new stock, which pops out from from anything, and then it might disappear the next day. Should I invest it or not? I just don't know anything about it. So this is the message beyond this story. And in particular, what I wanted to, okay, so, oops, how to get, oops, yes. And this is, if I just order them with respect to Shannon entropy, I will clearly see that, okay, if I want to get some gain, I want to get some predictable stocks. I should choose stocks with rapid fluctuations. It's mostly the energetic companies. They are mostly stable, or they are mostly predictable. I can think that I know how they behave. And vice versa, the companies with a low mobility of prices, they are worse in a sense that I can lose all my money if I invest them into them. The most popular, like Amazon and others, are somewhere in between. Okay, so that's what I wanted to say. That is the example of data analysis. A particular question, then you might estimate the amount of predictable information you could, or amount of knowledge you can learn from the data, simply by modeling, by modeling, particularly by model it by a Markov chain. A very simple example, but this is a strategy for learning strategy. And well, the outcome is that more predictable information, the more mobile and apparently uncertain behavior might give you more certainty about the future because it's predictable. You know how to work with it. Okay, so this is a message. Well, is in many cases, again, the data arrays which you would get from your customers might be real junk. They might not have any information. And then you, well, should be able to explain it, or at least to understand how much you can get from this data. Okay, so that's what I wanted to tell you today, guys. So I stop sharing. Yes, and okay, see you next time.